We're going to talk about conductors and electromagnetic waves. In this first video we're going to consider some general properties, and then after that we'll go into some slightly more detailed properties in the second video. So we're going to start from a simple statement of Ohm's law: J is equal to sigma E. I've put together a video of that which explains why you can get there from the Drude model of conductivity. And remember here that sigma is the conductivity. J is the charge, the current density, and E, of course, is the electric field. And we're going to combine that with the continuity equation, div J plus d rho by dt is equal to 0. So I have another video on that if you want to look at it. Again, it seems to be, it's based on the fact that in this universe that we have in front of us, charge isn't created or destroyed. That gives us the continuity equation. And we're going to assume that we're in a linear material, in which case we can write that the divergence of D, which is the free charge, which is what we're going to be interested in, and then we're going to substitute in and say that's a divergence of epsilon E. Let me make that epsilon just a little bit more epsilon-like. And that's going to equal rho free. So the divergence of E is rho free over epsilon in this case. So let's substitute that into, let's do some substitutions into the continuity equation. What we have is that d rho free by dt, and my f's are starting to look a little bit like t's, so I'll write that more carefully, is equal to minus the divergence of j. We've just written that j is sigma e, so we now have minus the divergence of sigma e. And if we pull out the sigma, we get that's minus sigma div E, which is simply minus sigma rho free. Again, my F needs reworking, over epsilon. That is a very simple first order differential equation. So what we would typically write is the integral of d rho free. I'm going to make it a full differential over rho free is equal to minus the integral of sigma over epsilon dt, and therefore rho free is equal to rho free at t equals 0 e to the minus sigma over epsilon times time. And this is the well-known result that in the bulk of a conductor you cannot have any free charge. It will dissipate to the surfaces. The timescale over which it will dissipate to the surfaces we could write as tau, and that's going to be epsilon over sigma. That's a characteristic time for the dissipation. And if you think about other things which might be happening in the conductor, say with a frequency of omega, so if we're considering some process, of course in the back of our minds we'll be thinking about electromagnetic waves with frequency omega, or angular frequency of course, then what we're saying is that tau should be very much less than 1 over omega in order for the dissipation of free charge not to interfere with whatever process we're considering. And that implies that sigma over epsilon omega should be very much greater than 1 for this redistribution of free charge to happen significantly faster than whatever process we're thinking about. In a real material, if you use that very simple rule, then you come up with something like 10 to the minus 18, 10 to the minus 19. Of course, there will be more complex processes, but typically it'll happen on the time scale of femtoseconds or tens of femtoseconds. So that's about the dissipation of charge in the bulk. So now let's think about what actually happens to an electromagnetic wave when it reaches a conductor. We start with the wave equation, the full wave equation. So we have del squared E minus sigma mu dE by dt minus epsilon mu d2E by dt squared is equal to 0. And that's derived from Maxwell's equations. If we assume that the E field is written simply as E is equal to E0, E to the I k dot r minus omega t, i.e. a standard plane wave, then we can substitute that into the differentials and derive the following equation. We get minus k squared, that comes from the del squared E. We get plus I omega sigma mu plus omega squared mu epsilon equals 0. So del squared E gives us the minus k squared, because when we differentiate the plane wave twice we get down a k squared and we get an I squared, which is the minus sign. dE by dt gives us a minus I omega, but then there's a minus sign here, so we have plus, and then d2e by dt squared gives us an omega squared. Of course the minus minus gives us 1, but then there's an I squared which cancels with that minus sign and gives us that final plus omega squared mu epsilon. And if we then rearrange that, we get the following dispersion relation: k squared is equal to mu epsilon omega squared into 1 plus I sigma over epsilon omega. We can also write that as k squared is equal to mu epsilon omega squared plus I times sigma mu omega. So the reason I've written that second form is that it helps us to see what's happening. This is the standard linear dispersion relation, k is equal to omega over c. This extra term is something which comes from the fact that we've got a conductor. And as ever in physics, if we have two terms, we want to think about two limiting cases, one where the first term dominates over the second term, and vice versa. Clearly, the thing that will determine the difference between these particular behaviours is going to be related to sigma and omega. And in fact, let me just get rid of that, what we can say is that if sigma over epsilon omega is very much greater than 1, then in this 1 plus I sigma over epsilon omega, the sigma over epsilon omega term will dominate, and so we'll have what's called a good conductor. And you'll notice that that's the exact same condition that we derived up here from the continuity equation and Gauss's law. It's reassuring to find those things. Something would have gone rather wrong if they differed. If we were to sketch that, we would find the following. I'm going to be assuming that we're doing a log-log plot here. And we're doing, that's gone too far, that'll do. What we're doing here, so we're doing the logarithm of k, or it can be log base 10 if you prefer, it doesn't matter, and then the logarithm of omega. And so what we'll have along here as a dotted line is the simple linear k is equal to omega over c. We will have another line here, which I'll do in green, which is the limiting behaviour of, let's say, that is k is proportional to the square root of omega. And the reason I'm doing that is because if you look at this term and that term, then in the case of k is equal to the square root of omega, we've got a good conductor. And let me draw the lines in black. We have to think about real and imaginary parts. And what we find is that for low frequencies, we start going along the green line, and then the real part will come along here. And let me do the imaginary part in red. What we'll find is that the imaginary part comes along here and then plateaus to a flat value. That's just a basic description, and so you see that down here at relatively low frequencies, we have what you would call a good conductor. And then up here we've basically shifted towards linear behaviour. So there's a transition. So even things that we think of as good conductors will change their behaviour with frequency. One more thing just to mention is that we define different velocities for waves. So the phase velocity Vp is equal to omega over k. The group velocity Vg is equal to d omega by dk. And we'll think about those at least briefly when we consider the properties of conductors more. And when you discover that they're not the same, then that's a clue that you've got dispersion, which is a change away from the linear relationship between k and omega. In the second of these videos, I'll look a little bit more at what happens with good